Hello, everybody. Welcome back. I know I was talking about at the beginning of the last episode that there were some updates to this tool that I'm using, but there was an update that changed most of the changes back. So these last videos should be pretty normal. Um, so we're into chapter 13 now. We're talking about partial differential equations. And instead of me solving a partial differential equation for you guys today, I'm instead going to derive one and kind of show why it's important. So yeah, we're going to be obtaining the heat flow equation, and we're going to be using the specific heat and thermal conductivity equations. So the book gives different hints for this problem, but I don't find them all that useful, so instead this is how we're going to do it. Okay, so the specific heat equation might be something that you learned in like a chemistry class or a thermodynamics class. Um, it tells us that the change in energy, in this case heat, of an object, um, so the amount of heat going out from an object is equal to the mass times the specific heat of that object times the temperature change. So the reason why that negative sign is there is because when the heat is leaving the object, your temperature lowers. So a positive amount of heat leaving an object means a negative amount of temperature rise, so a temperature drop. So let's take the limit of this. Differential amount of heat equals negative m times c times differential amount of temperature. And so we're going to divide this by dt. So when we do that, what we get is dq dt equals negative m times c times del t, or del t. That's del because our temperature also varies with position and not just with time. And then just as a notational thing, I'm going to write dq dt as q dot. That's how it's often written. A dot means a derivative with respect to time. So yeah, q dot equals negative m times c times del t del t. Okay, we'll be back to this equation, but we'll leave it there for now. And now we're going to use the thermal conductivity equation. Um, so the second law of thermodynamics tells us that heat flows from a hot place to a cold place. So let's say that we have some sort of thing where this is our temperature axis and this is our distance, like an x-axis or something. So if we have, our temperature does one of these things for whatever reason, uh, what the heat flow does is the heat will flow from a hotter place, like here or here, and it'll flow to a colder place. So it'll go down, so the heat will go down into there and try to raise up the temperature basically. So that's what the thermal conductivity equation tells us. And the steeper the slope of this, the more heat goes. So, up here it might not be going as much, but as it goes down, as the temperature gradient rises, or I guess as the temperature gradient falls, the amount of heat flowing into those places rises. So, for example, a curve like this, you might have a little bit of heat, but a curve like this, you're going to have a lot of heat flowing right across there to try to even out the temperature difference. That's not all it depends on. It also depends on the thermal conductivity of the object, which is why it's called the thermal conductivity equation. So something that has better thermal conductivity, it'll take a gentle slope like this, and if it has very high conductivity, it'll still flow in large amounts over even over a small temperature difference. So all that being said, this is what the equation actually is. So Q dot, this is the same Q dot that we're dealing with earlier, over the amount, so Q dot per area that you're interested in equals negative temperature gradient. Actually, yeah, temperature, actually, yeah. So negative K, which is your thermal conductivity, times your temperature gradient dot, sorry, I'm gonna put parentheses here to make it easier to see. This is dot, and your normal vector to that area that is over here. So your heat flow per area is your negative conductivity times the temperature gradient dot your normal vector. The gradient here turns the scalar temperature into a vector gradient, and then you dot that with the normal vector. That becomes a scalar again. So you're really dealing with a whole bunch of equations of scalars, except for the fact that the normal vector does have to have a direction. The normal vector is also has a uh, magnitude of 1. So so this is the thermal conductivity equation, but this isn't quite the form that we need it in. We would prefer, instead of dealing with areas, we'd like to deal with volumes. So we're going to use basically the divergence equation, which is something that is also covered in this book, but way back in chapter 6. So this basically says that if you're interested in knowing, let's draw a little box here. Yeah, box. It might not be the prettiest box, but that's fine. So we have a box. And we're interested in something flowing in or out of the box. So the one of the ways that you can tell how much stuff is going in and out of the box is to look at, let's say you're facing it head on. So you're now viewing this face here. How much is going in this side and how much is going in out of this side. So if there's a smaller amount, so you take the difference between the two of them. And then if you want to find that, this would be like your dx. So you evaluate it here and you evaluate it here. You take the difference. So all that to say, you do the same thing on all the other sides. And then when you do that, you shrink it down to a single point. And what that gives you is it gives you the divergence operator. So all this to say, I don't really want to get into the whole technical explanation of all this, but all this to say that this equation here turns into, so you can sum over the area to get your total Q. So your total Q, I'll just go ahead and write that out. Your total Q dot is equal to negative K A. This equation only truly holds when everything is constant. So you have to do an integral if it's not constant. So that turns into Q dot over V equals negative K, and then you take the divergence operator, or the divergence of whatever your vector function was. In this case, it's our gradient of t. So, but since you're taking the divergence of a gradient, that just turns into the Laplacian operator, which is that operator squared. So So now we have our heat heat flowing per unit volume instead of per unit area. Um, so and yeah, a more detailed explanation can be found if you look up the divergence theorem. It'll give you all the details. Um, so what happens with this equation then? Because we have two equations that look similar on on one of their sides. We have the q dot over here, and we have the q dot over v over here. So what happens when you take the q dot or the let's make this equation look like this equation and see what we end up with. So if we take q dot, let's divide this equation by our volume to make it look like that. So we have q dot over v equals negative m over v times our specific heat times the time derivative of our temperature. And this is mass over volume. You all should know what mass over volume is. That is our density, rho. So minus rho c del t del t. So we have two things we have two equations that are the same on one of their sides. So now we can set them equal to each other. So I'll just do that here. Negative k Laplacian of t. And I'll rewrite this down here. Laplacian of t is equal to rho c over k dt or del t del t. And this is what we wanted to find originally. We wanted to find that the Laplacian of t was proportional to del t del t. But not only did we find that, we found out how it is proportional. So this is the value. This value here is usually referred to 1 over alpha, where so alpha is equal to k over rho c. And this is called the thermal diffusivity. So it's highest in metals and lowest in nonmetals and like organic materials and such. And it's a measure of how fast temperature diffuses. How fast the temperature goes away as far in distance and all that. So this this only holds technically because of what we were doing up here with all this. This only technically holds when your density, your specific heat, and your thermal conductivity are all constant, which is a useful model. It's not necessarily the most accurate. Obviously, you know that density changes with temperature. Your specific heat will also change with temperature. And also, your thermal conductivity can change with temperature. This is a thermal conductivity chart here from one of my favorite textbooks. And you can see that it's not constant with temperature. But it is a useful model. And once you have these models here, you can usually change them or in some ways to make them more accurate if you need to. And if you find out that an approximation is good enough, you can write a paper on it and send it to me and let me know and I'll read it. So thank you so much for watching. This series is wrapping up, coming to a close. Still have one more video for you guys, and I hope you guys will stick around and watch it. And thanks for watching this video.